Hello everyone, I'm Ryan Keeley, a postdoc at UC Merced. I'm here today to tell you about why there cannot be a low-redshift only solution to the H0 tension. So in general, I'm interested in trying to test the lambda CDM model, trying to pull it apart and see where it breaks. This model is pretty remarkable in that it can explain a bunch of pretty novel physics with just 6 parameters, from inflation to Big Bang nucleosynthesis to recombination to reionization, the growth of large-scale structure, and to the late-time acceleration of the universe. It's pretty non-trivial that these 6 parameters fit these diverse datasets at all. So there are a few different ways to pull at lambda CDM and its assumed GR, but today I'll focus on testing the lambda part via low redshift distances. So one measurement where lambda CDM may be coming apart is with the H0 tension, which is a mismatch in the value of the present Hubble rate as directly measured by the Cepheid calibration of supernova distances, and the value as inferred from the lambda CDM-based inference of the CMB. This mismatch has reached a statistical significance of over 5 sigma, and while there's no obvious systematics, the way to detect the need for systematics would be via independent measurements of H0, for example with gravitational wave-centered sirens, or time delay distances, or calibrators of supernova distances other than Cepheids, like the tip of the red giant branch. However, the tip of the red giant branch is not as precise as yet. Lensing time delay distances need more systematic control, gravitational standard sirens need more electromagnetic counterparts, and so the final word on this is yet to come. However, the more interesting resolution to the tension is new physics. These solutions often come in two not mutually exclusive categories, whether the physics plays a role at high redshift and low redshift. And to be clear, by high and low redshift, I mean pre and post recombination. So common low redshift proposals include curvature, evolving dark energy, dark matter-dark energy interactions, and common high redshift proposals include ineffective, early dark energy, interacting neutrinos, features in the primordial power spectrum, and primordial magnetic fields. So important datasets to begin to sift through all of the different proposals are the supernova and BAO datasets, often called the guardrails of the tension. So the supernova, or type 1a supernova at least, are empirically assumed to be standardizable candles. That is, the supernova with the same light curves marginal of the color and stretch of the supernova, as well as properties of the host galaxy, have the same intrinsic luminosity. This intrinsic luminosity, parameterized as MB, is degenerate with H0 and is unknown, and so on their own, the supernova cannot measure H0. One needs an independent calibrator like the Cepheids to do so. The BAO dataset measures the positions and riches of galaxies, which can then be used to reconstruct a correlation function. The correlation function contains a BAO feature, which is an overdensity of probability at a drag scale RD, and thus the BAO feature can be used as a standard ruler to measure cosmological distances. The constraint on the distances from the BAO datasets are expressed in terms of dm over RZ and dh over RD. Thus, the BAO are also uncalibrated and do not measure H0 on their own. So what's shown here are the BAO data points along with the Planck predictions alone, as in not adjoint fits. So taken together, the BAO and supernova datasets map out the shape of the low redshift expansion history. And one important thing to keep in mind for this talk is that they are consistent with lambda CDM. So what is shown here is a posterior of the hyperparameters of a Gaussian process regression. So this GPU regression uses a set of random functions to fit the data, and sigma characterizes how different the random functions are from the best fit lambda CDM expansion history. So the fact that the posterior of these hyperparameters is consistent with 0 indicates that the data prefer no deviations away from lambda CDM. So why might low redshift solutions have been expected? So for one, the CMB does not measure H0 on its own, it only predicts it. And from the CMB to the Cepheids, this is a projection in order 3 orders of magnitude in scale factor. So it was perhaps natural to expect adding new physics between the CMB and today could solve the H0 tension. So for further, low redshift solutions are useful since the physics at the CMB is non-trivial, and such solutions at low redshift would inherit the high redshift successes of lambda CDM. Also, since the CMB constrains H0 via the constraint on theta S, low redshift solutions need only contend with geometric degeneracies in the CMB. And thus there could exist a W of Z such that the CMB is well fit and predict basically any value of H0. Okay, so what do we need to include if we want to robustly rule out low redshift solutions? Since the datasets are basically just geometric datasets, they just measure distances, we really only need to parameterize the Friedmann equation. And one simple way to generalize the Friedmann equation away from lambda CDM is to allow the dark energy equation of state to vary. And so the goal here is to come up with a parameterization for the dark energy that would bracket all of the low redshift solutions that agree with the data. The most common parameterization for an evolving dark energy is the CPL. So CPL typically evolves away from a constant W of Z only at redshift of 0. And it is this feature that we want to generalize. We want to allow for an evolution in W of Z at any redshift. So thus we parameterize the equation of state with Chebyshev polynomials, where x here goes from z equals 0 to the redshift of the surface of last scattering. So the case I want to make is that this parameterization is flexible enough that it cannot offer a satisfying solution to the H0 tension, then there can be no low-redshift solution. First, I want to make the case that this Chebyshev parameterization is flexible enough to mimic common equations of states. Two such models that we explicitly check are the TDE model and the Payday model. These two models are useful for making this point since they represent two opposite regimes of a slowly varying, purely phantom equation of state with the Payday model, and a quickly evolving equation of state that transitions between a phantom equation of state and a quintessent equation of state with the TDE model. Further, we use two examples from the CPL parameter space that are within the 2 sigma confidence region of the Pantheon plus and Planck constraints. We can see that the Payday model equation of state can be matched basically exactly, but the TDE equation of state is a less exact match. However, the corresponding H of Z and DM of Z values are all within less than 0.4%. In addition to comparing with specific models, another useful test to demonstrate the flexibility of the Chebyshev parameterization is whether it can bracket the data. That is, whatever cosmological functions that may still be allowed by the data would find a sufficiently close match in some location in the Chebyshev parameter space. To this end, we calculate a posterior predictive distribution for the Chebyshev model constrained on just the Planck CMB data. The distribution spans the data indicates that this model is flexible enough to contain a low-redshift solution to the H0 tension should one exist. Here we see another way to show the flexibility of the Chebyshev parameterization. The blue curves here are W of Z functions drawn from the posterior of the Chebyshev parameterization constrained by the CMB and H0 dataset. The takeaway from this distribution is the variety of W of Z functions that can achieve a high H0 value consistent with the Shoes constraint when you also have the CMB constraint. One additional thing to notice is that most of these have a phantom crossing. Now that we have demonstrated that the Chebyshev parameterization should include any potential low-redshift solution to the H0 tension should one exist, we now test whether one does actually exist. To do this, we constrain the Chebyshev parameterization using the CMB plus BAO plus supernova datasets and compute the posterior of H0. If the posterior from the joint constraint of the CMB plus BAO plus supernova dataset spans the H0 constraint from Shoes, then with this model, the joint CMB plus BAO plus supernova datasets would not be in tension with the Shoes datasets. Then we would properly calculate a joint CMB plus BAO plus supernova plus H0 constraint and conclude that the Chebyshev parameterization offers a satisfactory solution to the H0 tension. Conversely, if the joint H0 if the constraint on H0 from the joint CMB plus BAO plus supernova datasets is still in tension, then we do not calculate a joint constraint with the Shoes H0 dataset, and as the results would be meaningless. So the results of this test are shown here in green. So unfortunately, we see that the Shoes constraint lies entirely outside of the posterior predictive distributions. Indeed, we find that H0 is 68 plus or minus 0.8, 68.08 plus or minus 0.97, which relaxes the tension but does not offer a satisfying solution. Thus, the Chebyshev parameterization does not solve the H0 tension, and by extension, no instance of new physics that only plays a role at low redshift would solve the H0 tension. So here we show the corresponding results in terms of W of Z. The green curves are W of Z functions from the posterior of the Chebyshev parameterization constrained by the CMB plus BAO plus supernova joint dataset. So that these curves converge around W of Z is equal to -1 shows that these datasets prefer no deviation from lambda CDM. There is still a lot of flexibility still allowed in the phantom regime, especially above Z of C greater than 1. This is, after some thought, a rather obvious point. So there are two effects that come into play. So above Z greater than 1, the data become less constraining for both datasets. And so one can observe that an increased scatter in both DH of Z and DM of Z, but also above Z of 1, the dark energy is becoming less of a dominant component of the expansion rate, and so the dynamics of its equation of state is less relevant for the fit. Indeed, for the same value of W of Z is equal to 0, W of Z equals to 2 can vary from -1 to -2, with only a small change in the log likelihood. Okay, so now I want to discuss why lower redshift solutions to the H0 tension are insufficient and seek to develop intuition about what features a successful solution to the H0 tension would satisfy. Any proposed solution to the H0 tension is a prediction that the proposed extended parameters are correlated with a high H0 value. So here we see how the extended parameters of the Chebyshev model are correlated with the standard lambda CDM model. This figure shows the posterior for the Chebyshev model using the joint CMB, BAO, and supernova dataset. The Chebyshev parameterization is complicated, but the important part of it when fitting the CMB plus BAO plus supernova dataset is W of z equals 0, basically the value of the equation of state that is most stringently constrained by the data, basically because the supernova data are very dense around z, is around 0.1. So for this parameterization, a high H0 value requires W of z equals 0 to be less than -1. And at the same time, a high H0 value requires a low omega matter value to satisfy the constraint on omega matter h squared from the CMB. So especially taken together, a low W of z equals 0 value and a low omega matter value make a 4 fit to the supernova data, which drives the fit towards z equals 0 of -1 and omega matter of around 0.3. So it's ultimately the supernova constraint that rules out much of the Chebyshev parameterization's extended parameter space. Shown here are constraints on the Chebyshev model using the CMB, BAO, and CMB plus BAO supernova for both the Chebyshev and lambda CDM models. So one might look at this triangle plot and think that there does exist a point in parameter space where the gray overlaps the olive, which overlaps the green, and thus that there would exist a solution to the H0 tension. However, these plots are a projection of a large dimensional posterior onto 2 dimensions, and in this higher dimensional posterior there is no overlap. So basically, the beyond lambda CDM parameters that the Planck posterior that shifts the Planck posterior towards the Chu's constraint are different from the ones that expand the BAO plus supernova posterior. For the lambda CDM constraints, the CMB, BAO plus supernova, and Chu's constraints create a tension triangle, which results from the 3 constraints never overlapping at any one point. This tension triangle evidences the need to modify RS as part of solving the H0 tension. That the Chebyshev constraints on the CMB and BAO and supernova expand towards Chu's constraint, one might conclude that modifying RS is in fact not needed. Indeed, the Chebyshev parameterization breaks the generosity between RS and H0. However, the full CMB plus BAO plus supernova constraint for the Chebyshev model shrinks away from the Chu's constraint, indicating the expanded parameter space does not alleviate the need for modifying RS. Similar to the last slide, here I show the CMB, BAO, and supernova and Chu's constraints, show how they can create a tension triangle also in the parameters H0 and omega matter. Such a tension triangle has been advanced as the reason why simply modifying RS cannot fully resolve the H0 tension. So from the CMB, the parameter omega matter h squared can be measured relatively independently of low redshift physics. So this fact is why the Chebyshev constraint from the CMB lies basically along the line of degeneracy of omega matter h squared as being a constant. The flexible Chebyshev parameterization breaks any degeneracy between omega matter h squared and H0 that would exist in the lambda CDM model. And so a similar story unfolds between H0 and omega matter as with H0 and RS. So between the lambda CDM fits, there's no parameter where the CMB, BAO, supernova, and Chu's constraint overlap. So even relaxing the CMB constraint via the Chebyshev model only creates a narrow overlapping region at the edge of the 2 sigma region for each of the constraints. So when the BAO plus supernova constraint is relaxed via the Chebyshev model, there is a large region where the 3 constraints overlap. However, when we look at the combined CMB plus BAO plus supernova constraint, it does not overlap with the Chu's constraint because the region of the extended parameter space that allowed the CMB constraint to expand towards larger H0 values is again different from the region that allows the BAO plus supernova constraint to expand towards lower omega matter values. Okay, so here we try to answer the question, what would the results be if we didn't include the BAO datasets? This is in part answer to the question, so what now makes some of my previous solutions, like the transitional dark energy model, fail? So to fit both the H0 and CMB constraints, a successful model that adds physics at low redshift must have a faster than lambda CDM expansion at low redshift and a slower than lambda CDM expansion history at high redshift. Of course, the simplest instance of this feature would be a purely phantom WZ, but to further fit the supernova well, the model would need to have to account for the fact that the CMB plus H0 constraint is pulling to lower values than allowed by the supernova dataset. So to counteract this effect, the W of Z can transition to a quintessent regime. Particularly, the transition is constrained to be at Z is greater than 1. So the region where the supernova were less constraining and the BAO constraint did not extend to at the time. So such a transition from a phantom to a quintessent regime is what gave the TDE model its name. However, for models like TDE, it's ultimately the BAO constraint that the model fails to explain. So particularly at the high redshift Z greater than 1 BAO measurements constrain H of Z to be around lambda CDM values where the transition was previously happening. So those BAO measurements basically rule out the final slice of parameter space that allowed the TDE model to work as a satisfactory solution to the H0 tension. And thus you can see here, if you don't include the BAO dataset, you basically get back similar TDE kind of models, which you can more explicitly see here, where basically the phantom crossings in the orange would basically be relatively similar to the TDE model. Okay, so that leads me to my conclusion slides. So that even with a very flexible model, such as the Chebyshev parameterization, that basically brackets the entirety of the relevant space of model uncertainties and can fit every relevant cosmological distance, there exists no point in the extended parameter space that adequately explains the H0 tension. Thus, since this model brackets the entirety of the low-redshift space of model uncertainties, its inability to find a solution to the H0 tension indicates that there is no satisfactory solution to the H0 tension that adds physics at only low redshift. Thus, the community should look for high redshift modifications of the standard lambda CDM model to provide a satisfying new physics solution to the H0 tension. Thank you for your time.